real pleasure to be here to speak today. I have roughly 40 minutes worth of presentation, assuming that it goes the way it normally does when I do this. So what I would like to do is take questions through the chat, and we will pick them up as we can as we go along, and then hopefully towards the end of the presentation there will be an opportunity for about 15 minutes worth of Q&A, and we can have a more far-reaching discussion. This is the first part of a two-part presentation that I have given a number of times across the country. Second part actually talks about the tools that you can use to do risk assessment in an infrastructure context. So this part is more of an introductory seminar on the concepts of vulnerability and of risk and risk management and general concepts of that type. So we'll get into that. Leading from this, then we would perhaps as a second webinar down the road go into how the tools are structured to address this kind of these kinds of issues. I'm established before these presentations a set of guiding principles. One of them is that the climate is changing. I state this normally because I've been in a lot of presentations and a lot of situations over the years where this becomes a point of contention, and it's a great topic for discussion. It's one that I really like to have usually in the bar over a beer after a seminar, and we can have a lot of fun with it. But for the purpose of this presentation, our assumption is that it is changing, that climate change is actually compromising the ability of engineers to safely and effectively design infrastructure to meet the needs of Canadians, because it's calling into question the current rules and design standards that we use as engineers to design infrastructure, and it also suggests that we may need to change the way we design, operate, and maintain our infrastructures. Climate change engineering vulnerability assessment is one tool that we can use to help us in that process, and so it's not as bleak as it may sound in the first two or three bullets of this. There's a lot of tools available to help address it, and this is a large part of the work that we at Nodal Core through Engineers Canada and Natural Resources Canada have been working on. We define always our terms before we get started. Public infrastructure are those facilities, networks, and assets operated for the collective public benefit, including health, safety, cultural, or economic well-being of Canadians, whether those are operated by government or non-government agencies. So it could include private companies that are running infrastructure for the purpose of the public benefit. Engineering vulnerability I'll define here, and then I'll redefine it or emphasize that definition as we move through the presentation. Engineering vulnerability is a shortfall in the ability of public infrastructure to absorb the negative effects and benefit from the positive effects of changes in the climate conditions used to design and operate infrastructure. It's a function of the character and magnitude and rate of change of the climatic conditions to which infrastructure is predicted to be exposed, and I emphasize the word predicted. And it's a function also of sensitivities of the infrastructure to those changes in terms of its positive or negative consequences. It's also a function of the built-in capacity of that infrastructure to absorb any negative consequences from the predicted changes in climatic conditions. We'll talk a bit more about that in a few moments. And therefore, when we talk about engineering vulnerability assessment, we're requiring an assessment of all of the above: the nature of the climatic change, how sensitive the infrastructure is to that change, and how much built-in capacity that infrastructure has to absorb that change. So I've done some definitional stuff. Something that I always like to spend a bit of time on is this concept of what engineers believe, and I think this has a big bearing on how we go at doing vulnerability assessment and those kinds of activities, because it's based on fundamental belief systems that we engineers have ingrained in us from the day we start going to school. And here are some of those concepts. That the past predicts the future, so that by observing how things behaved historically, we can predict how they ought to behave going forward. We also believe as engineers that scientific principles always apply, that thermodynamic laws don't change, Newtonian physics is constant, and therefore this gives some solidity and some basis for the thinking that we do as we approach design and operation and maintenance activities. And finally, we believe as a profession that problems can be solved with logical reasoning, that the physical world is not irrational, and that observed phenomena can be explained. So we believe in a rational, concrete world where with good logical reasoning we can observe and make predictions on how things ought to behave. However, there's some things that are not stated in that belief set that we need to come to grips with as a profession and as people who operate infrastructure and systems for the public good. First is, the past is not the future. I've been challenged on this statement in the past, but basically people say, well, if it's not, then how can we predict? And the answer I have is that the past is an analog of how we expect future events to transpire. That is, if things happen this way in the past, it's reasonable assumption to assume that they will behave that way in the future. But in actual fact, the only 100% certain future event is the one that's actually occurred. Now, this is a pretty philosophical statement, but it really comes into play when we start talking about risk and risk management. Because when we talk about risk and risk management, we're talking about future events and predicting those events in a way that is rigorous and scientifically justifiable. The other thing that we need to understand is that scientific principles can only be applied in the proper context. That is, the right tool for the right job. So, you know, you would not use thermodynamics to solve a Newtonian mechanics problem and vice versa. So we need to understand that as rigorous as our science may be, it needs to be applied in the proper context to solve the proper problem. And finally, one of the things that I think is fundamentally true is that when we use our logic to solve problems as engineers, it only really works when our assumptions are correct. And so in many cases where we're looking at failures or potential failures, the logical sequencing, the logical processes that we use to do the assessment are absolutely pristine. It's beautiful logic. But there are problems in the way in the assumption we made or in some of the data we've used, and that can skew the result. So we need to be aware of that reality and how that affects the way we as engineers think about problems as we approach them. So from a climate perspective, I like to show this slide and show basically what that kind of past is not the future thinking can mean. This slide shows a temperature profile since the year 1000 and predicting through the year 2100. The data up till about 1900 or in the late 1800s is, you know, from ice core data. It's inferred data from other measurements, and it's reasonably consistent over that time frame. Then the data between roughly 1900 and the year 2000 is measured data, it's thermometer readings as recorded over time. And the data from 2000 to 2100 is data that's based on data that's based on modeling from the IPCC. So I'm going to answer a question here. Nicole, I'm not sure how to give you moderator privileges. Is that up to me? Anyway, I'm going to carry on with this, and we'll go from here. So this is basically what the temperature profiles look like. If I, as an engineer, assume that the past predicts the future, then I'm likely to draw a line on this curve that looks something like this. I'm going to take some of the more recent data, I'm going to look at some of the historical data, and I'm going to make an assumption likely that it's reasonably consistent and horizontal. Now, you can debate whether I've drawn that line in the right spot on that curve. I teach at the University of Alberta, and I've showed this curve to one of my engineering classes, and of course they got into the debate as to whether it's in the right spot on the curve given the statistical relevance of the data and the like. But for the purpose of this this exercise, what I'm saying is that you're likely to have some sort of a horizontal line. You're going to take historical data and trend it forward on that basis. If we took, however, the current trend as predicted both by current measured temperatures and what the models are likely to present, you're going to see a curve that looks something like this. And there's a significantly different forecast of future temperatures. Now, from an engineering perspective, I would say that the area between those two lines is an area of unquantified risk. I really don't know where in those lines reality lies. As a matter of fact, I may have drawn the 45-degree line at the wrong angle. It might actually have to incorporate some of the more extreme climate modeling results. So I have an area on the curve where I'm not really sure where our future events might lie in terms of temperature. And this presents risk in terms of how I design systems that depend on temperature data. I want to spend just a few moments talking about the nature of failure, because this has a big interplay in how we look at risk. Failures can occur from very small changes in final events. So this is data from Australia, and it's very revealing, and it shows that a 25% increase in peak wind gust data, peak wind gusts can cause a 650% increase in building damage. This is significant, and we've been challenged on this data in the past, and that's prompted us to do some thinking about what does that really mean in terms of potential for failure. What it says is that small increases in weather and climate extremes can have the potential to bring large increases in damage to existing infrastructure. And I will spend a few moments in the upcoming slides talking about why that might be. And it says that climate change could significantly impact infrastructure depending on the robustness of existing climatic design values. So if I've used good, solid data regarding future temperatures, then I should be okay. Or if I've designed my infrastructure in a way that it can absorb significant changes in temperature, I should be okay. But we need to think about those kinds of things as we're looking at our infrastructure designs. So I asked myself the question, how is it that small changes can lead to catastrophic failure? And this has been my experience in the energy sector, doing a large number of failure analyses for the energy sector over the years. And what we find is that usually it is a very small final event that leads to a significant loss of service or catastrophic failure. And so why is that? And so in terms of an infrastructure mindset, when we design something, we have in mind a capacity of that infrastructure. We have in mind what is the number we need to design for. We design to that number. Then, being a bunch of conservative engineers, we add a safety factor on top of that. So we not only design for what we think it ought to handle, but we often add margins on top to accommodate, as a conservative errors in our design. Maybe we had some problems with our load considerations, whatever, and we do that. Now, over time, aging on the structure will lead into some of that margin. That's one of the reasons why we add it. This is just normal aging, wear and tear on the structure. If we add on top of that some unforeseen weathering events. If you think of this in terms of a road context, greater freeze-thaw cycles than we may have anticipated, then not only would you see the normal aging on that infrastructure, but you would see additional weathering and wearing on the infrastructure that is eating into the capacity. Now, based on the slide I'm showing at the moment, this is still okay because we're above our safety. We're still using our safety margin. Well, when we designed for design load, and you can see it in this case. We have additional capacity. Capacity was above the design load in the first place, and we still have a safety margin above that. However, over time, we changed the way we use infrastructure. An example of this is population growth, and we start to increase the load that we impose. In the energy sector, we often do projects, bottlenecking projects, where we will actually use some of the safety margin up to increase the profitability of the organization. So we'll actually push equipment harder. But it's okay because we have that safety margin and we're still operating within a safe zone of operation. However, if we then have a severe climate event, and in this case this is not a significantly severe climate event, it's a reasonably small one over the entire load range of the infrastructure, you can see that load is now exceeding capacity. And when that occurs, we're in a failure mode. When load exceeds capacity, systems break. Sometimes they break catastrophically, sometimes you experience a loss of service, but in any event, you enter into a failure mode of operation. We're no longer do we have the capacity to handle the loads that we're exposed to. And it can be caused by a very small increase, a very small event at the end of the day. So observations about that. A small change can have a dramatic impact on infrastructure. Design safety margins may not last through the full operational life of an infrastructure system. They can be consumed by day-to-day uses and activities, or we may actually use them up ourselves by the way we operate. And that failure often arises from a combination of events, many of which we don't normally monitor. So when we get into the realm of risk management, we have to consider the broad range of things that could have an effect on that infrastructure, not just climate change, not just normal use patterns, not just the increased use pattern. It all has to be taken into account. From a climate change perspective, one of the observations is that climate change can affect both the load and the capacity of the structure. So it can increase the load through its climate events, but it can also wear away at infrastructure and eat up the resiliency of that infrastructure over time. However, because we're looking at small events causing these failures, it suggests that even small changes in the way we operate the infrastructure can mitigate the risk. So sometimes changes in maintenance practice, and sometimes just ongoing measuring and monitoring activities, knowing what the infrastructure is actually experiencing compared to what we think it ought to be based on our design. A little bit more definitional material. We defined vulnerability with a very long slide with lots of words on it earlier. I wanted to show here what it means in terms of load and capacity based on a similar set of slides to the ones we just looked at. So if we take a look at this case, we have in an engineering design scenario, we forecast both load and capacity on a structure. In this case, we're forecasting that the load on this structure is going to exceed its capacity. So we're predicting that there's a gap between our forecast capacity and the forecast load. And we are identifying a potential future failure condition. And I use those words carefully because this is forecast. Since the past is not the future, we are anticipating these changes, but we need to get a sense of how likely this actual gap actually is. So when we identify such a gap in this risk, this kind of work, we call that gap an engineering vulnerability. So the gap is the vulnerability, the difference between our forecast capacity and our forecast load. Okay. So Nicole, I've lost the ability to advance. Oh, there we go. Bit of a lag there. Okay. If we can predict, however, that there's a safety margin between the forecast capacity and the forecast load, we identify potential future non-failure conditions. In this case, we have a margin, and this is how we as engineers hope to design. We hope that there will be a margin that allows us some safety factors, the ability to absorb some events, the ability to absorb some additional use on the capacity, etc. So in the work that we do, we call this resiliency. This is the ability of that infrastructure to absorb change, whether it be climate change or other changes associated with the use of that infrastructure. Just a bit of an aside, and I'll move forward. How can we assess vulnerability and resiliency? Well, Engineers Canada, in partnership with Natural Resources Canada, has developed a protocol to lead practitioners through a formal documented process to identify vulnerabilities and resiliency. And if you wish, at the end of this call, we can talk a bit about how to access that protocol, how to talk to people who worked with it, and get involved in perhaps some case studies with it. The protocol that we've developed applies standard risk assessment processes to this new concern. So it's using what we understand to be, from an engineering perspective, very standard processes, and we're applying it to new issues, new concerns. A few more observations. First, that vulnerability assessment is predictive, so we are contemplating potential future modes based on forecast information. And the question that always comes to mind when you're doing this is, how much confidence do we have in that prediction? Because that confidence dictates how much money at the end of the day, how much effort, resources we're willing to allocate to fixing this potential problem. So we need confidence in our predictions. So in order to effectively address the issue, we need to assess the likelihood of the event and the level of service disruption, whether that be very minor or whether it is catastrophic failure resulting in complete loss of service of some sort. Without this assessment, there is insufficient context to properly manage the issue. And I put in big letters here, risk assessment, because this is in the realm of risk assessment. In risk assessment, what we spend a lot of time looking at is, how likely are these future events that we're talking about? And if they should occur, what is the consequence? What's the level of service disruption? Are people going to be hurt? Those kinds of questions. So we spend a fair amount of time contemplating these two elements. And like I said, this is a standard process of risk assessment. And this is why when we do vulnerability assessment, we use risk assessment tools. I'm going to step back now and say, we said at the beginning that the past is not the future. And I just want to address, and this is for, once again, mostly for the engineers in the crowd, because when I say the past is not the future, we get alarmed because engineers use historic information, observations, to design safe structures for people to use going forward. So if we have very little confidence in a historic record, then we lose a lot of confidence in our ability to design, and that's not good. But what we are saying here is that even though the past is not the future, it can be used to forecast the future with the following, when it meets the following criteria. One is that it's based on an accurate understanding of the historical record. So we know what that data is really telling us. That we apply appropriate scientific analysis to that data. We don't just take an average and apply an average. We take a look at what that means and how it fits into ongoing scientific work on the subject. And finally, that our assumptions that we're basing on all of this work have been verified with real-world observations and our experience. So in the real world of engineering, we have to get our hands dirty and see how it actually worked and how it's working to make those kinds of past observations work for future work. However, simply extending the historic record forward does not forecast future events. And our view of this is that it's simplistic and it is pretty risky. And we need new tools to quantify and manage risk on a go-forward basis. So that's why we're doing this. Our historic record's important. We need it. We can't abandon it, but we have to understand it, and we have to apply it with a certain degree of scientific rigor and due care. Well, risk assessment tools and techniques help us quantify risk. So this is why we use them. Once again, the Engineers Canada and Natural Resources Canada Engineering Protocols, one such tool to do this. There are others, and there's a lot of work going on at the moment to address these issues. The Engineers Canada Protocol is the one that we've had a lot of involvement with. It's been applied in 8 case studies across Canada, coast to coast to coast, with a large degree of success. And so it's one we're confident with. And so it's one we can talk about a bit later on as we get into the discussion. But when I talk about risk, I came back to this. What do I mean by risk? What is risk? And that's an important thing, because we use the word risk pretty loosely in day-to-day conversation, and when I, as an engineer, use the word, I'm using it in a very precise, analytical way. And we need to understand that difference and the implications that can have on communicating risk issues. Well, technically, risk is defined as the product of the probability of an event and the severity of that event, and the important words here, which I've emphasized, should the event occur. So you have to treat these things as separate entities. The probability is one thing, the severity is another, and then we can come up with an estimate of what the actual overall risk is. What we find is that the average person can be very confused by these concepts, and that confusion falls into 2 categories generally, and these are the boundary conditions, and then of course, talking like an engineer, these are boundary conditions, and there are elements of this in covering the entire spectrum in between. But first is confusion is risk being equated with the severity of the event, and the second is risk being equated with the probability of the event. I will just expand on this just in a little bit over the next couple of slides. When we equate risk with severity, we have the following considerations. Severity is a magnitude of an outcome. It's usually stated in negative terms, and it's often defined in terms of personal injury. So what it says is that severity could mean there's an insurance loss of $1 million, or somebody was physically hurt. Maybe there's death involved. We talk in terms of those negative outcomes, and that defines the severity of this event. Sometimes people confuse the risk of an event with the seriousness of the outcomes. Thus, you'll hear this said that nuclear power will absolutely, and this is what happens in this kind of discourse, will absolutely cause China syndrome events or nuclear explosions. So, yeah, those kinds of things could possibly happen in the nuclear industry, and we've seen some examples of nuclear accidents. But the assumption that underlies this statement is that because they have happened in the past, they will absolutely happen when we build this particular project in this particular location. and that clouds the discussion. Or another example is that greenhouse gas emissions will absolutely cause events such as those depicted in the day after tomorrow. Well, day after tomorrow shows a lot of very serious consequences resulting from climate change. It shows very serious outcomes, but it doesn't really talk about how likely those outcomes are. And so it creates a scenario where when we talk climate change, we're talking about doomsday. And that's not really talking about the risk. It's talking about the outcome, potential outcome. So this approach neglects likelihood of events. And so what tends to happen when people fall into this trap is that extremely unlikely events can be treated as very high risk. And so we make management and business decisions potentially based on a very serious but highly unlikely outcome. And that's probably not too good. The other thing that tends to happen in normal day-to-day conversations is that we'll equate risk with probability. So this assumes that high probability events are always high risk, and low probability events are always low risk. So it neglects consequences of those events. So, for example, people might say, I don't need to wear a seatbelt because I never have accidents. So this is saying that because it's highly unlikely that I'll have an accident, that I'll never need to wear a seatbelt. Well, the fact is that although it's unlikely, it is still possible, and in that event, you may well want to be wearing that seatbelt. Or nobody is getting sick from drinking that water. Well, maybe very few people are, maybe historically they haven't, but that does not mean that people might get sick from drinking that water going forward. So it's saying that because it is unlikely that it's not important, and that's not good risk management. It's characterized by statements like, that will never happen, and we've actually heard this statement in some of our risk management workshops where we'll talk about a scenario where something may impact on an infrastructure, and the answer is, never happened, so we don't need to worry about the consequences. And the answer is, well, maybe we ought to contemplate those consequences, because if it ever did happen, it would be very serious. So unlikely events may be high risk if the severity of the outcome is very high. So we need to contemplate both the probability of an event and the seriousness of that event to get a real sense of the overall risk that we're facing. So like I say here, since risk is the combined effect of probability and severity, both elements must be considered. And very low likelihood and high severity events can be a serious risk, while very high likelihood and low severity events can be a very low risk. I've noted in working in this field that most people have a really good, solid, intuitive understanding of risk, but we often need guidance to sort out and assess the relative significance of likelihood and severity. I mean, I think of personal examples of this where if someone wakes up once in a while with a minor headache, they say, take a painkiller, I'll get on with my life, it's not very serious. If that headache, even though it's minor, occurs 3 or 4 times a day over a period of a month, then even though the severity of the headache's not high, the likelihood is very high, and we start to treat it with much more seriousness. So we understand intuitively that low severity events with high recurrence are potentially serious. And conversely, we understand that low likelihood events that are very serious can be very serious events. So if I wake up with a very serious migraine headache, I'm going to treat it with some concern, and I would be concerned even though that didn't happen very often. These are intuitive understandings of risk. The work that we do in engineering analysis attempts to put some numerical context around that intuition that we all share. And the protocol that I have discussed briefly throughout this presentation guides people, practitioners, through a process of assessing both probability and severity in a rigorous manner. So like most standard risk assessment protocols, it will ask questions that demand you answer these, segment and answer these elements separately. Just a few more slides, and then we'll open it up to some discussion. This slide shows a standard risk matrix, and what it shows is along the vertical axis, the severity of an event. On a scale of 0 to 7, this is an arbitrary scale. It's the one we use in our protocol, but it could be a 0 to 10, it could be a 1 to 5, it could be high, medium, low. It's depending on how you want to go about setting this up. And similarly, on a similar scale, probability of that event on a similar 0 to 7 scale. So what we've done is we've used a numerical analog for severity and probability in this case. You can also use, financial loss. You can use likelihood of events in terms of what your historic record might have shown and the like to get at this. But for the purpose of this exercise, not too worried about how we establish these severity and probability scales, more so than that we have set them up and what that would tell us in terms of a risk management scenario. So in this case, I'm contemplating a flooding event. It is very low probability. On the chart, it's between a 0 and a 1. It's very low probability event. But should it occur, it's really serious. But because it's so low probability, it is showing up as a combined risk assessment as a low risk event. Well, if the climate changes in such a way that the frequency of that flooding event changes, the 1 in 100 year event becomes the 1 in 10 year event, for example, then what you can see happening is that the flooding event, even though its severity has not changed, its probability has increased significantly, and that has shifted it on our risk matrix from a low risk event to a very high risk event. High risk being indicated by the red colors on the chart, medium risk by the yellows, and low risk by the white. So in this case, we've shifted this event from a low risk event to a high risk event, not by changing the severity of the event, but by changing the likelihood of it occurring. So in some of the climate change scenarios, these are the kinds of things that we're contemplating. Well, if you undertake an adaptation measure for this flooding event, building floodways, increasing the levees, doing zoning restrictions in areas, those kinds of things, you can reduce the severity of that event at that location. So it's now no longer causing the same level of financial loss. Maybe it's not causing the same level of disruption it might have had. We've undertaken some kind of action to reduce the severity. Even though the probability of the event is the same, we've now reduced the risk. And so it becomes a low-risk event again, even though it is high likelihood. What this means in terms of the work that we do in risk management is this. There's a difference between vulnerability assessment and mitigation action. And so in vulnerability assessment, what we are looking at is assessing the change in risk. What events, what circumstances are affecting this structure in a way that can change the risk associated with operating it, the risk of climate change, the other risks associated with this infrastructure. When we are assessing that change, we call that engineering vulnerability assessment. To this point, we've made no recommendations on what can be done to fix it. We're simply assessing the level of concern. The next step is risk mitigation. And with any good vulnerability assessment, you are going to want to identify potential actions that can be taken to deal with the identified risk. We should never simply identify a risk and leave it at that. If risk is serious, then either we identify a need for doing additional work to mitigate that risk, or we provide some recommendations as to how to get on with fixing it. That piece of work, which can be engineering, it can be management, it can be scientific studies, it can be a combination of things, it can be management actions, is called risk mitigation. So with every good engineering vulnerability assessment, there is a next step that involves risk mitigation. And so when we talk about doing risk assessment, even though I have focused entirely through this presentation on identifying, what the risks may be, what the likelihood is, what the severity is, there is an implication, an implied next step that says we need to go further than this and identify how to fix it, because unmitigated risk is a serious liability. So I'm going to break this presentation up at this point. I just want to point out that if you want further information on infrastructure engineering vulnerability assessment, the type that we're talking about here, or participation in a vulnerability assessment case studies, or other work in this area, you can check out this website. It's for an organization which we affectionately call PIVC, which stands for the Public Infrastructure Engineering Vulnerability Committee. It's a high-level committee involving government and non-government organizations from across across Canada and across all three levels of government. And this group has done 8 case studies on infrastructure vulnerability across Canada, coast to coast to coast. So they're very good to look at the website, see some examples of case studies, or if you're seriously interested in pursuing this further, you can contact my colleague David Lapp at Engineers Canada, and I've given you his contact telephone number and his email address. I'll leave this slide up for just a moment, but I'm ready to start taking questions. I'm going to turn my microphone off so I can hear what any questions there might be, and you can also raise them through the chat, and we have roughly 10 minutes for ongoing questions if there are any at this point. So I will turn off my microphone now, Nicole, so you can take the lead.
Does anyone have questions for Joel at this time?
So I'm not hearing any audio questions. I'm willing to wait for a minute to see if there are other inputs. Okay, I got 1 of 17 hands raised, and I have a question from, I think that's Taraka 5. Would it be possible to give a real example of how to reduce the severity of the risk? Yeah, there's I think a really good example using my flooding case study. This is historic, but if you think about the design and building of the floodway around Winnipeg to deal with city flooding, the severity without the floodways, of course, that large parts of the city of Winnipeg were flooded. As a child, when I lived in Winnipeg, it was not an unusual event to see flooding in the city, and then after they built the floodway, it's a much more rare event. I mean, they still have flooding issues in that part of the world, but the floodway has gone a long way to reducing the severity of those events. And so, yeah, there's one real-world example.
putting sewers.
Great, that's good. And you can raise your hand as Nicole has shown you to ask questions if you wish. I will close the microphone once again to see if there's any thing that Nicole wants to say.
You can go ahead with your question.
Yeah, the question is, would you compare the cost of mitigation with the cost of insurance before making recommendations? That is, well, I'm going to give you the engineer's answer, and it depends on where you're at in the process. Certainly, after a risk assessment, I would identify that there is a need to take some sort of action, and if there's a logical management action, we would recommend that. But in the long term, absolutely, you would want to evaluate your options. Not just from an insurance perspective, but in terms of, so you'd look at insurance requirements, you would look at the engineering cost, you would look at, in some cases, you might look at the cost of eating the failure on an ongoing basis and just making the repairs as time goes by. You may institute management actions, and you need to kind of look at all of that before you can make a final recommendation on this. But so there are recommendations that you would make right after the assessment that identifies the risk, and then there would be much more robust recommendations that you would make after further engineering and management deliberation. Yeah, and my business partner also indicated social cost as part of the consideration in there as well. So, especially when we're talking about public infrastructure, loss of service may be a minor repair from a cost perspective, but could be major disruption for businesses relying on that service. So, Nicole, I'm open for a couple more questions. We're pretty much close to the hour. I'm happy to stay if there's dialogue to go on, and or go with the flow from here. So I'm not seeing any questions. I'll make one last call, and then for questions, if you want to ask a question, put your hand up, and then I'll know to stop talking and listen to what you have to say, and we'll go from there. Okay then, Nicole, I'm going to turn it back over to you to close off. I don't see any additional questions at this point. If people have something that they want to ask, it occurs to them after the fact, they can either email me on the address shown on this slide, or they can approach David Lapp through the contact points I gave on the previous slide, and we can help you out with both the technical side of this and looking at if there's an interest in pursuing how to go about getting involved in case studies and the like. The other thing I would like to ask people to think about, and that they could get back to Nicole, would be if there is an interest in seeing the second half of this type of presentation, where we actually delve into the tools that are used to assess risk and talk about it in a much more focused way. How do you go about doing this, as opposed to what is it? So Nicole, turn it over to you and let you finish this out.
So if there isn't any more questions, I would like to thank you, Joel, for doing a wonderful presentation, and I'd also like to thank all the participants for coming out today and listening to the presentation. Thank you.